Okay, section 1.7, rate equations. Now, we've done a bit about rate of reaction before in AS, and the focus there was looking at how temperature affected the rate of reaction and looking at activation energy. The first part of this is very much looking at how does concentration affect the rate. Okay, so change in concentration. Effect on the rate of reaction. Now we need to just define what rate of reaction is a little bit more precisely than we have done before. What we're going to say is if you've got a reaction, reactant turning into products, well, the rate is the change in the concentration of the product with time. So how quickly the product is made with time. So that would be change in the concentration. Square brackets means concentration of course. Change in the concentration delta over delta T, the change in the time. So how much product is produced in a certain amount of time. So the units of rate of reaction, which we haven't really talked about before, should be concentration per time. So that's going to be mole dm to the -3, concentration seconds to the -1. Alternatively, rate can also be described as how quickly the reactants disappear. So you can also have rate is equal to minus, because the concentration is always dropping of the reactant, over time. It's okay to describe it that way as well, and be the same units, mole per decimeter cube per second. All right, let's have a little think about a reaction such as we've got, let's say we've got magnesium plus hydrochloric acid goes to magnesium chloride and H2 gas. So how would we measure this rate of reaction? Well, you've always got to look for something changing, and probably the most obvious way of doing this would be to, because you're making a gas, hydrogen, would be to collect the gas in a gas syringe. So you'd have your gas syringe there. Connect that up to this is the flask containing the reaction. So there's your acid and your magnesium in there. It's a bit of magnesium ribbon. And you'd hit that. Okay, so that's the basic, and you measure the rate, so how quickly the hydrogen was produced with time. And if you did that, you would get a graph, something like this. Okay, let's say here, for the sake of argument, let's say that the magnesium is in excess in this case. Right, so here is, you haven't got enough acid to react with the magnesium. You've got volume of hydrogen here against time, and you get something like that. I'm sure you're familiar with that sort of graph. So you could see about here, you say that the reaction is finished, isn't it? And the reason why it would be finished, I've said that the magnesium was in excess, all the acid has run out. How could you work out the rate of reaction from this graph? Well, the rate of reaction, it would be given by the gradient of the slope of the graph, yeah? The gradient. So at this point here, the gradient is 0. No more hydrogen is being produced, the rate of reaction is 0. Where would be the rate be the greatest? Well, the rate would be the greatest at the very start. And as soon as the reaction starts, the gradient gets less and less and less as you go up. Yeah. Now, why is that? Well, it's because you said the magnesium is excess, so the rate decreases because the hydrochloric acid concentration, the concentration of that will decrease from the moment the reaction starts. It will go lower, and of course we know if you have a lower concentration of reactant, the rate of reaction is going to slow down. So that gets us to this idea. We want to talk about the rate. Really, we want to talk about initial rate. Because we know as soon as the reaction starts going, the rate of reaction decreases. It's very important we want to know about the initial rate. Why is that? Because it's the only, and that's i.e. time is equal to 0. It's the only time when we know the concentration of HCl. If we think about here, we don't know the concentration of HCl. Let's say we started off with this concentration was 2 mole per decimeter cubed to start off with. We don't know what the concentration is here because some of it's been used up. We know it's less than 2 moles per decimeter cubed. We don't know what it is. The only time when we know the concentration is at time 0 there before the reaction has actually started. So that's why we were interested in the initial rate, because we need to know the concentration then. Now, how do we find the concentration? How do we find the initial rate of reaction? Well, we need to draw a tangent to this curve, don't we? Okay, so draw a tangent, something like that. That's a tangent to the curve at time 0. And then what we need to do is need to work out the gradient of the tangent, okay? Now, how do we work out the gradient? Well, we do draw a little triangle on your graph paper. And we want gradient is equal to the change in y over the change in x. And in this case, it's going to be the change in, so that's going to be the the volume of hydrogen, the change in the volume of hydrogen divided by the change in the time. So here, this is going to be the time, and this is the vol H2. So that is what we're going to be interested in a lot of the time here. So we're going to do experiments where we end up with initial rate against the concentration of the reagents. So a lot of the focus of this topic is actually doing experiments which enables you to do that, find the concentration, how that affects the initial rate. How does it change the initial rate? So we know that from a previous experience, when you increase the concentration, you increase the rate. But what we haven't really thought about before is, so if I double the concentration, will I double the rate, or will it be different? If I double it, will it be something else? And that is the focus of this topic, which we'll cover in the next video.